Hello everyone. We are Team 248 and yep, we are the last group but not the least important of this DS4A Colombia 6 cohort. And this time, our project aims to detect segments of power transmission lines where exists risk of failure, and thus be able to define the critical distances to scan risk points using LiDAR technology data analysis. We want to ask you have ever considered your lives without electricity or living having continuous blackouts or power outages? Many of you will answer that it's something impossible because today the energy service in most of the country is reliable and at the same time basic as having water or internet. However, to guarantee day by day that the electrical service has the current reliability throughout the country, there are so many operations, maintenance, and other processes that we have no idea of their existence, and those processes turn in economic cost which is included in the rate for service users. In this case, we'll talk about ESA, a company with over 54 years of experience that operates in sectors like the electric power, roads, telecoms, and ICT business in several countries of LATAM. But ESA Intercolombia is so important in Colombia because they control about 72% of the country's energy transmission and operates more than 11,000 kilometers of electrical networks distributed mainly in the Colombian Andean region. Knowing now the important role that ESA has in Colombia's electrical network, just as any other company, ESA has various challenges to accomplish. They have to maintain the power transmission system running 24/7 and pursue the maintenance optimization in the process. In order to accomplish this, ESA is interested in taking advantage of the use of new technologies using new tools that can provide faster diagnosis of failures, which means a higher quality service along Colombia. The use of new tools not only means innovation, but managing and interpreting big data sets through data analysis. The challenge that ESA has is the elaboration of an artificial intelligence application that can detect and classify any risk that could lead to power transmission failures. Having this application, ESA could optimize maintenance by planning them according to the level of risk detected by the app. The main problem faced by ESA is the difficulty to predict power transmission interference. External objects causing inappropriate contact in the power line generate failures and interruption. Usually these objects are trees or vegetation. Unfortunately, the prediction of vegetation interference cannot be exact due to several factors such as the lines passing through different types of trees, different climates, environments, for which it's difficult to predict the growth of these objects. Therefore, it is very important to have data on objects that may create possible risks due to their current distance. One solution that ESA has given to this problem has been scanning the power lines with LiDAR in order to see the lines without having to send a crew to these inaccessible areas and saving money as well. This is why our team took on the task of analyzing the LiDAR data to detect and classify risks along power transmission lines. Okay, now getting into the data, for this case we have to talk about a light and distance detection technique called LiDAR. This device allows, by combining GPS with laser sensors, to make three-dimensional maps of the forests around the electrical network and also map the lines to check if the distance between the forest mass or any nearby object and the power lines is correct. After the scan process with the LiDAR scanner, the data is stored as a DATLAS extension file, which contains X and Y as a position and C representing the sea level. Those are points of our orthophoto that allow us to digitally represent the 3D map and get information about the objects detected by the scanner. In this case, the data provided by ESA were 11 documents per section and 10 million rows per document. Now, looking for a solution, these packages were used in combination to explore and present results for data. The most important ones are Plotly, which is a tool used to generate interactive and well-descriptive graphics on Python, and Dash, which is a service built into Plotly that allow us to create web-based interfaces to enhance data presentations much better than regular BI tools.
The data extraction process It started when ESA Intercolombia used a helicopter to fly over the power transmission lines using a lighter laser. The laser beam bounces on all objects and returns to scanner with the object position. At the end, the data is saved with records of coordinates, color of the points, and height of the objects. Two final data sets were obtained, a last file and a file given by the lighter laser, and another file with each object identified. The last file is processed by a Python code to extract the color of each point. That way we can project the object with its correct colors. That result is joined with each point classification in one dataset. After that, we will use an algorithm to calculate the distance in meters between all object points. This is crucial for all the following steps. Since the risks are related to the power lines, we identify the points that represent those power lines and calculate the 150 nearest points to them. If the distance is too short, we will identify it as a high risk, but if the distance is very high, in general, more than 8 meters, the risk will be low. We used this risk classification table to classify and label risk based on distance in relation to the class of objects around the lines. Well, here we have the web application to detect risk in power transmission lines. First of all, here to our left, we can see the control panel where we have two drop-down menus. In our first menu, we can select the different lines to update the map. Each item belongs to a specific track of the power transmission line, while in the other drop-down menu, we can select a section within this line. Each line is divided in sections of approximately 1 million points scanned by LiDAR. If we scroll down, here we have the map where we can visualize the different lines. This map updates according to the selection we make. Let me show you. Perfect. Here, as you can see, the map has updated, and we can interact with the map and its points. As an example, here is a power transmission tower. Down here, you can also see a road, different types of terrain, and different types of vegetation. Below the map, you can see that if you want, you can select a point in the map so that the application gives you the exact coordinates of the point. Here, you can see the value of each coordinate, and it is automatically transformed into latitude and longitude points, which allows the technician to see the exact point and place where the risks are detected. We click here on Map, it takes us to Google Maps, where we can see the exact coordinates. So we're back to the app. In the map, we can see the different risks which are identified in different colored cards. High risks are in red cards, medium risks are in orange color, and low risks are identified in yellow. As we hover over the map, we can see some yellow points that mean low risk. Or here, an orange point that means it is a medium risk. Okay, now let's see a heat map. Here we can see the distribution by the different level of risk, low, medium or high. And we can see a types of risk, vegetation or terrain. This heat map is specific to the section selected. This would be all for our application. In conclusion, it was possible to obtain the expected results given that it is possible to graphically represent the points in which they exceed the allowed limit, throwing the expected alert, and this will allow us to exactly locate the point or set of points in the geographically area where the risk is located. It is now for further application to apply this to the entire national power transmission system through a hosted server. Thank you for your time, and this is Team 248.